I'll do the share screen trick and pull up the slideshow if all goes smoothly. Let's see here. That would. I see it's not in the right place, but we can fix that.
There we go.
Oh, if everybody would turn off their mute themselves, that would be helpful. If you don't, I will go ahead and mute you because I have that ability.
I know we started here last time, but I like this picture. Besides, Franco missed it. A couple of things that I jotted down for introductory. One is I do have this program that I must have taped it from the library. It's a video lecture series by David Christian. David Christian is Mr. Big History. I think he coined the term. It's called other things. It's called The Journey of the Universe. It's called The Great Story. It's the evolutionary story. I mean, it's what's understood now is that there is a story, that the universe is on a journey. It's changed greatly over time. It's not done. Same is true for the planet. David Christian's very good. He's a professor in Australia. He was at University of San Diego for a while. Anyhow, I have this program, and it's called The Big Bang: Life on Earth and the Rise of Humanity. David Christian, $520. I'll make you a special deal. I can give it to you. I would give it to you for free, but if you want it, you need to get a flash drive to me that holds 50 megabytes. That's big, but it's not so big anymore. It's less than a gigabyte. But if you want it, I'm watching it for the second time, and I really enjoy it. Especially, the whole story gets a lot more interesting, I think, when life is initiated, like the evolutionary story of life on the planet, which I'm just getting to on Christian. I'm also rereading A Short History of Nearly Everything by Bill Bryson, and I think it's the third time I've read it. It's a great book. It's just a great book. I highly recommend it. He's so entertaining, and yet he is telling the story of our story, the evolution of life. It's just very well done. So we have these themes that come out again in this slideshow. I just want to dwell for a moment on this word emergence, which I'm very fond of, this word emergent. We live in an emergent universe. There was nothing or almost nothing. And as I said last time, now check it out, look around. I mean, I just look out the window. And I think emergence it's a big factor in the great apes. Humans are a great ape. And there were no apes, and there was no genus Homo, and there were no Homo sapiens. It's a journey. And so what I'm saying is, as a word of encouragement, is the issues that humanity have, and they are serious issues, is part of the journey and part of trying to find out how far we can go with the stupendous emergent properties of Homo sapiens, like love, like caring for creation, like intelligence. And I mentioned David Steindl-Rast. He says we can be grateful. We can open our eyes and be grateful that we have eyes to open. I like that a lot. So on we go. You aren't actually there because you cannot take a picture of the Milky Way because it's 100,000 light years across, and we don't have that kind of time or travel capacity. This is the Andromeda Galaxy, which must be the nearest galaxy to the Milky Way. And I can tell you an odd thing about the Andromeda Galaxy. If you learn how to do it, you can see it with your bare eye, especially on a clear night in winter. Close to Cassiopeia, the constellation Cassiopeia, it's not anything to see. And I guess that's the interplay of reality and the mind. If you didn't know it was there, you wouldn't see it. It's just a slight fuzz patch, much more easily seen with binoculars, but you can see the Andromeda Galaxy. Yeah, so we didn't know that the Andromeda Galaxy existed until 1925 when Edwin Hubble identified it. And he identified many of the points of light out in the sky with a telescope, visible with a telescope, as galaxies. We didn't know until 1925 that there was more than one galaxy in the universe. That's less than 100 years ago. So this journey we're on is constantly unfolding, and there are no other great apes or mammals or reptiles or amphibians pondering these questions. You know, we have a special assignment to wake up to the wonder of the evolutionary journey that we're a part of. So it was not known there were any other galaxies. You know, the number jumps around. It's now, the number that I see now is 2 trillion. Now, I don't know what would put a limit on it, but it thought, you know, that you could, if you Google it, you'll find it said that there are 2 trillion galaxies, 100 billion to 400 billion stars in each galaxy. It's, you know, it's just beyond any potential for comprehension. It's 2.5 million light years away. If traveling at the speed of light, it would take 2.5 million years to get to the Andromeda Galaxy. That's not going to happen. That's okay. So I think partly, well, the people who are working on big history have put together a structure, because humans are storytellers. We interpret the world through stories, and they've made a story out of big history. And this is part of that story. I think it has a grounding in reality. And so what they've said that this big history journey has these 4 major themes, one of which is increasing complexity. And I think it's fair to say, you know, in the early universe after the Big Bang, the primary element was hydrogen and a little bit of helium. And just an example of increasing complexity, and we'll go into this a little further. Now there's 92 naturally made elements and some human made elements, and some enormous structures made out of those elements that did not formerly exist. That's an example of complexity. All these things have emerged. They did not exist. Apparently, I mean, it seems very likely that the universe emerged and is on this journey. There are some mysterious aspects to it that science calls Goldilocks conditions, the Goldilocks effects, where it's astonishing how many things are just right for life on Earth. And they are not just right for life elsewhere, even in the solar system. You know, the center of this, this surface of the sun is about 7,000 degrees. The center of the sun is something like 20 million degrees. It's just not the condition for life, but we live in the habitable zone, 93 million miles from the sun, thanks to everything being just right. The universe goes through thresholds. I think I have these. Oh, this is, well, I have a list of the thresholds, but there are some major changes. I know the first, there was no universe, and then there was a universe, as Brian Swim likes to say. Well, that's impressive. There were no stars. That's the second threshold. We'll come to those, but as an example that there are these major thresholds. If there are no stars and then suddenly stars ignite, something big has changed. Can't remember. Complexity, I think. That's a hydrogen atom, 1 electron and 1 proton. That's most of what there was in the universe in the early days, with a little helium. And now we have things as complex as the blue whale, which is the largest organism to ever live on the planet, and is estimated to have 100 quadrillion cells. And the cells themselves are made up of 100 trillion atoms, not just hydrogen, atoms made by fusion in stars and supernova explosions. So increase in complexity over time. There's the proof. The elements have emerged. There was only hydrogen and helium. Now there's 92. The big history story is that they were fused in the center of stars, or the larger elements, actually everything past iron, which is number 26 over there on the right, which means 26 protons in the nucleus, were fused in supernova explosions, which, geez, I had the number, I don't have it. The temperature in a supernova explosion is almost inexpressible, far beyond the temperature in the sun. I mean, it's billions of degrees. And the pressures are great. And these, in a process that most of us could never understand, the smaller elements are compressed together and fused into larger elements. So our sun is a red giant star, and it's fusing hydrogen into helium, and will go on at least as far as oxygen, but it doesn't have the gravitational capacity and pressures and heat to go beyond that. And it will, of course, burn out at some point, as all stars do. In fact, the hard blue stars burn out a lot faster, but they have more fuel. They burn more rapidly, but they make elements further along the periodic table. So, Goldilocks effects. There are many things. I think the list would be possibly endless of things that are just right on Earth for life to exist. And if they were altered slightly, life could not exist. And the sun is one good example. The Earth is just the right distance. It's in the habitable zone, 93 million miles from the sun. The sun is the right kind of sun. It has a moderate amount of fuel compared to stars that are 10 times larger or 100 times larger, which burn much faster and much hotter. Yeah, the rate of burning fuel, it's, the estimates is that our sun has burned for 5 billion years, 4.5 billion years, and will burn for another 4.5 to 5 billion years. Strangely, I mean, the information, the facts of this evolutionary journey, many of them are, I think, they're incomprehensible. They lead to just a sense of awe, and I assume they're right. And what I'm thinking of at the moment is the sun. If you look it up online, the sun is said to be burning 600 million tons of hydrogen a second, fusing into helium. And yet it will last another 5 billion years. Well, that is a lot of hydrogen. And these are numbers that are not particularly comprehensible to us. So these are the thresholds that initially the big history people, David Christian, and the people he works with in various universities came up with, and I altered it slightly, and I think it is somewhat discretionary, and you can see what you think. You saw, some of you saw this last week, but this is worth reviewing. It's almost impossible to remember. So the Big Bang is a threshold. If there was no universe, and then there is, that's a big change. The stars ignite. Stars ignite because there's these massive gas clouds of hydrogen shooting out from the acceleration of the Big Bang into the universe. If it was, there's slight unevenness in the distribution of the hydrogen, so that gravity starts to pull the hydrogen atoms together. Every hydrogen atom will affect every other hydrogen atom, depending on how far away it is and the amount of mass, which isn't much, but it has gravity. And as Brian Swim says, one hydrogen atom started to take an interest in another hydrogen atom. It's gravity. Everything attracts everything else, and started to pull these hydrogen gas clouds together. And once it started, there would have been increasing proximity of hydrogen atoms pulled more tightly together. We're talking uncountable numbers of hydrogen atoms. It got so crowded, they're crashing into one another, that they started to fuse. They ignited. And let's see, what did I read? That why does it give off energy? It gives off energy because there's less mass in the helium that is created. Not much less mass, surprisingly little. But a tiny amount of less mass in the helium atoms than was in the hydrogen atoms, and that is converted into energy, and is the energy given off by the sun. The elements are created, We talked about that a little bit. They're fused in stars, they're fused in supernovas. You can't have planets. You can't have much of a planet if there's only hydrogen and helium. You need larger elements with different chemical properties. And so you had to have the elements created by the stars before you could have planets. Then planets began to appear. We don't know how many planets there are. There are plenty of planets out there in the larger universe. Life appears, that's considered a threshold, clearly. Life is something different. It's out of equilibrium with its environment. It has a different internal chemistry and energy flow than the external environment. And it has capacities that non-life doesn't have, and it appeared, and it's not known where life came from. So then, as I said last week, I changed this a little bit. For David Christian has humans, and it's just, we can't help but be fascinated by Homo sapiens, but I think photosynthesis is a major threshold in the evolution of the dynamics of the planet, because that's where all the food comes from. 99.9% of the food. Homo sapiens appear in abstract thought. All thought, by the way, is abstract. You can't just put thought, though. You have to put abstract thought. But it's a major player. This phenomenon of thought we need to observe, because it is abstract. Thought is not the planet. Krishnamurti says the word tree is not a tree. You can think about a tree, but that's not going to be a tree. And I think it's one of humanity's foibles, is that we're lost in our thinking to a detrimental degree. We're missing the moment. We're missing the intensity of the moment. And that would come perhaps that would be intelligence. So this is a little bit of my own overlay, and you're welcome to make your own list of thresholds. But intelligence would be waking up to a miraculous planet, and an ecological planet that is intimately interrelated, so that we are not the separate beings that we seem to be. We're part of a flow of life and non-life that once we wake up to that, and there are people waking up to it, and maybe they can help the rest of us, I think the human situation on the planet will be much better. So we're actually going to talk a little bit about geology. We're trying to get the Earth created today, so that next week we can talk about life evolving on the planet. We can't talk about the origins of life because we don't know how life originated. But interestingly enough, for my own taste, to understand something about geology, I found that this phenomenon that we touched on this last week, but it doesn't hurt to review, this phenomenon of atoms having the electrons being in shells, orbitals, same meaning, different picture perhaps in your head, is critical to understanding how geology works. And so there are these orbitals. The first orbital, which is labeled S1 there, and I think I have the S1, it holds 2 electrons. Well, so hydrogen has 1 electron and goes in the first shell. Helium has 2 electrons, it goes in that first shell. Then that shell is full. If there's a third electron, it'll go into the second shell, which holds, and I can pull the number up here, holds 8 electrons. I mean, look at this order. We're talking about something that you can fit 10 quadrillion, I left the D out there, 10 quadrillion hydrogen atoms on the head of a pin. It has this intense precision and order. Where does this come from? No way to answer that question as far as I'm concerned. But we can be in awe that this is the nature of our universe. So there's that order. There's another element, and that is that for probably electromagnetic reasons, because we're talking about electrons and protons, both of which are electrically charged, atoms want their shells full. If it has a first shell and has 1 electron, it wants a second electron. Why an atom wants anything, I don't know. But that's the way it goes. 8. So Tuck would know those numbers better than I. I think it's true. The first shell holds 8, the second shell holds 8. I think the third shell holds 8, and then it actually holds 18. Yeah, I have that in parentheses, but it starts to overflow after 8. It starts to fill the fourth shell. So whatever, whatever works. So we're trying to move in on geology. Silica, silicone, the element silicone, which I think has 14 protons and 14 electrons. So it goes into the third shell. Carbon has 6 protons and electrons, and so it starts to fill the second shell. How many electrons will fit into the second shell? We know the answer to that, 8. How many are there? 4. How many more does carbon want? It wants 4 more. Why does it want anything? We have no idea, except for the reality of electromagnetic attraction. Look at silica. It's into the third shell, but how many more electrons does it want? It also wants 4. It has the same pattern. It's in the same column on the periodic table because it has the same chemical properties because of these electron shells, which what I find exciting is this part of atomic structure is highly understandable. I would think everybody listening can understand not why, but that it's a fact that the second shell holds 8, and the third shell holds 8. So if there are 4, they want 4 more. And you can start making predictions about what will join with what, how things will form, because this is the way that chemistry works. So CO2, carbon will join with oxygen, because it'll share electrons with oxygen. Oxygen wants 2 electrons, has 6 electrons in the second shell, holds 8. It shares electrons with carbon, but it becomes a gas, which is for mysterious reasons useful to life. What happens when silicone joins with oxygen? You get quartz. You get a rock. So while they have similar chemical characteristics, carbon forms a gas when it joins with oxygen, and silica forms a rock. So here's this is, I think, from Wikipedia: composition of the universe, atmosphere, Earth, animals, plants. So what we have here are some of the important, maybe I forget why I picked them out, important or dominant elements are on Earth probably, but I have them circled here. The Earth's crust. Look at the percent of carbon in the Earth's crust. It's 9/10 of 1%, 9/100 of 1%. There's almost no carbon. The interesting thing is, look at the human, I think next is, I circled human body. The human body is up to 60% carbon. Because life is actually made out of carbon dioxide, as I emphasized last time, and continues to stun me every time I say that. So one of the characteristics of life is it's out of equilibrium with the environment. I mean, we could look at the percent carbon in the atmosphere. Is that? Yeah, it's less. It's whatever that is, 1/1,000,000th or something up there in the atmosphere. Parts per million. Yeah, that's right. It's 100 parts per million carbon, not carbon dioxide. Most of carbon dioxide is oxygen. So we hear 400 parts per million. It's mostly oxygen. Okay, there's another thing. Some more circles here. Silicone. We're talking about creating rocks. The Earth's crust is 28% silicone. Silicone is silica. Silicone is the element. Silica is the mineral made with oxygen. But the human body is not interested in being made out of rocks, not made in. So similar chemical characteristics, but they respond very differently. But what we're doing is moving in on geology, and this geology, the story of geology is in part a story of silica, which is SiO2. So these rocks listed up there on the upper right: rhyolite, dacite, andesite, basalt. Everybody knows, we know what basalt is. The other ones might not be so familiar, but those are all volcanic rocks. They're rocks that poured out onto the surface of the Earth. What that graph shows is what percent of silica, SiO2, they are. I put silicone, it should be silica, SiO2. Rhyolite, which is the volcanic equivalent of granite, is mostly silica. Dacite is also mostly silica. All the rocks are at least 50% silica. And there are the other colors are other minerals, but silica dominates. Silica dominates the Earth's crust. So our shells again, let's see, I think we have another one here. This is just making silica from silicone and SiO2. So oxygen wants 2 electrons. And I forget exactly how it goes. I don't have the drawing, but somehow those electrons are shared so that silica has 8 electrons and the 2 oxygen have 2 electrons. So now we have a lot of silica and we're going to make an Earth. And particularly what we want to do is come up with continents. We haven't talked about that yet, but on the early Earth, there wasn't much in the way of continents. Continents have evolved and may continue to be evolving, which is a bit of a surprise. So we're going to come up with continents here. Well, these are characteristics of rocks. So on the left are rocks that have a high silica content. That would be granite. And down at the bottom, it says granite. It could say rhyolite, which is the volcanic. And the primary element on the very top where it says rock elements, oxygen, silica, SiO2. Over on the right, we have the heavy elements, magnesium and iron, low in silica. Well, there are rocks that are higher in iron, but they tend to be actually in the mantle. They're so heavy, like down at the bottom, it says peridotite. That is a mantle rock. It's almost never found on the surface of the Earth. It's high in magnesium iron. It's black, dark. High silica rocks are light. You look at granite, it's semi-white because it's made of quartz. Silica is quartz. So what are the characteristics of high silica content? Well, the important thing I want to point out here is silica often, not always, has a low melting point, and then it goes over to a high melting point. If these rocks are high in dense elements like magnesium and iron, they won't melt until it goes above 2000 degrees. Silica, especially in the presence of water, and there's a lot of water around, has a low melting point. And that is the beginning of an explanation for why there are more continents now than there used to be. So let's see, we mentioned Hubble figured out in 1925 that we were not the only galaxy in the universe. Well, I'm sure that was a blow. Because remember, prior to that, we had to figure out that we weren't the center of the solar system. And people were burned to death for suggesting that we weren't the center of the world. It's been a rough ride. And it continues to be a rough ride, right? I still want to be the center. Well, where was I going with that? Geology is similar. So it was 1925, we figured out we weren't the center of the universe. In 1900, we had no idea how the planet worked. Why are there mountains when everything is eroding? And they actually know the rate of erosion. I mean, the rate of erosion is such that the highest mountains ought to be a plain in about 50 million years. I mean, you've got plenty of time. Why are there mountains? Nobody could understand why they're mountains. Why are sedimentary rocks turned straight up in the air when they're laid down horizontal? What causes earthquakes? Why do the continents look like they fit together, which people had realized as far back as 1600, people realized that. Well, it was a long road to the answer, and a primary player was this man, Alfred Wegener, very impressive character in my estimation as I read about his story. But the two little globes shown lower left and lower right are from a drawing in 1858. Well, that's not the first time. So that's 50 years before Wegener was doing his work, before 1900 and 1910 and 1912. But it was suggested in 1596 that it looked by a man named Ortelius that it looks like the continents fit together. Antonio Pellegrini in 1858 drew these two globes and put the continents together and said it's obvious they were together. It's not obvious why they move. So Wegener did you all see that? They keep wanting to shut down my computer. Wegener did not originate this, but Wegener came up with the evidence that indeed the continents have moved over time, and I don't know how he managed to do this. Hopefully he didn't have to travel to all these coastlines, but he found closely related rock strata in South America and Africa, closely related animal fossils, and closely related plant fossils. And I think the same is true in North America and Europe. And he wrote a book in 1912 saying that he had the evidence that all the planets had been joined together at one point. I forget if he called it Pangaea. I don't think he did. He had a German name for it. Well, the problem here is that Wegener was a meteorologist. He was a weatherman, and the geological society of the planet was self-centered. They thought that they were the most important, at least in the world of geology, and they rejected his claim, said it was absurd, and there was no way that continents could move. That was 1912, 1915. He continued to accumulate evidence. He was killed in Greenland on an expedition in 1930. In the early 1950s, it was realized that there was a ridge, a high mountain ridge running right down the middle of the Atlantic Ocean. And it wasn't easy to figure that out. In fact, it was first, from what I have seen, it was first discovered in 1925 or 27, I forget which, by a German expedition. This is right after World War I. I don't know how they managed that, but they must have done it with depth soundings. They must have taken, because sonar did not exist at that time, they must have taken those measurements with a line and a weight. And they figured out that there was a ridge in the middle of the Atlantic Ocean. And I think they had a sense that there was magma involved with that ridge. And interestingly enough, so Wegener's weakness was he could not explain what force could move continents through the ocean crust. Although early on, he suggested a mid-oceanic ridge. And I guess that suggestion faded away in later works. This ridge was discovered by soundings in 1925, Wegener died 5 years later. Anyhow, then sonar was invented in World War II, and they got sound images of this ridge and realized that it had a trench in the middle of the ridge, that it was active. And the work, a point of interest here, as we're talking geology, but these aspects of human nature, of our hunger for identity, which most of us know what that feels like, and how the world revolves around the space between our ears. When I read that quote by Einstein in the first program, he said the whole project is to grow beyond that. And it's just not easy to do, but the reality is waiting for us, that we are just a part of a flow of energy and materials. They're not so important in ourselves. Anyhow, the first good image of this mid-oceanic ridge running the length of the Atlantic Ocean was put together by an American geologist, a female American geologist, Marie Tharp, in 1952 from soundings. She got these papers, graphics from sonar studies, and she put them together and realized the ridge ran the whole length of the Atlantic Ocean, and that it was an active geologic formation. And her boss, Bruce Heesen, said that was just silly girl talk. It was just silly girl talk because the females were not valued in the professional community. Once again, it's that search for identity has been like an albatross around the human endeavor. Anyhow, there is a ridge. The mid-oceanic ridge that runs down the middle of the Atlantic. I forget how long, but the ridge does not stop. The ridge goes all the way around the world, and the full ridge is about 40,000 miles long. I remember that much. And I think these basics, but they are crustal hotspots where magma is rising because it is 7,000 degrees down in the mantle. And heat just wants to rise, and it rises up through the upper mantle, pushes against the crust, cracks the crust. Magma is constantly pouring out in these rift zones, these mid-oceanic ridges. Meanwhile, the magma that has come out earlier cools. It's in the ocean, at the floor of the ocean. It cools, becomes heavier, and it's pushed to generally to the east and the west by this rising magma, pushed against continents. Continents are made out of lighter rock called quartz, silica. They're less dense. And the ocean crust usually subducts under the continents. I mean, we've been through this maybe once before, but this is a great image of the age of ocean crust, the age of ocean crust. The red, so the red are the youngest rocks, less than 5 million years old. And they get older and older as you move out. You look particularly clear is that Atlantic in the middle of the picture, the mid-oceanic ridge. The youngest rocks are in the middle, and then there's orange at, looks a little messed up there, 5 to 20. And then it turns to tan, white. They get older and older. The rocks get older, and then they disappear. They only get to, this shows them getting as old as, at the oldest, 160 million years old. More generally, 140 million years old. Doesn't matter. I've seen 200, but 200 to be pretty much the oldest. And then the ocean crust disappears. Where does it go? We know where it goes. It subducts under the continents and is recycled into the mantle and comes back out sometime in the future with the elements necessary for life that have eroded from the continents into the ocean and then are subducted over a long period of time, so that even the rocks on the planet are recycled and the nutrients necessary for life are recycled. So I hadn't noticed this the first time I looked at it, but look at the difference between the Atlantic and the Pacific. I mean, all I really noticed was the Pacific isn't very well centered, the mid-oceanic ridge in the Pacific over there on the left. But what else about it? Look at how much more active it is. The crust subducting under the Andes, under South America, is only 50 million years old. That is 4 times faster, at least, than the subduction rate in the Atlantic. Now, which is not an altogether accurate picture. As far as I know, and feel free to drop me a note if you know differently, I don't think there's any subduction under the east coast of North and South America. They are part of the same plate. They're attached to the same plate as the Western Atlantic. So they move together, and they are being pushed into the Pacific, which is why the Pacific subduction zone is so active, why the Andes are so tall. And there's similar levels of activity in Indonesia. Look at the colors in Indonesia, which that's so many earthquakes and volcanoes in Indonesia. It's interesting just studying it, looking at India, center right. You know, India journeyed. It broke off of Africa, spent at least 50 million years traversing the Indian Ocean, and crashed into Asia 50 million years ago, and is still pushing against the Asian continent, and the Himalayas are still uplifting because of that. I can't quite interpret that as well. Maybe that big brown section shows active subduction. Anyhow, so to return, the main point here is there's no oceanic rock that's more than 200 million years old. It all subducts. It's just totally active. The whole surface of the earth is active. This is just a nice picture that I was able to get of magma, of a heat plume rising up from the mantle to the crust, breaking through the crust, creating a rift zone. Most of those are in the mid-oceanic ridge, but there are hotspots on land, and one of them is Yellowstone. And Yellowstone has blown many times. I think the most recent is 600,000 years ago. And we'll talk a little more about that on another picture, but why is it hot? Oh yeah, this is Goldilocks. Down at the bottom, it says Goldilocks strikes again. Why is there all this heat? I mean, my feet were really cold yesterday. How can it be 7,000 degrees a few miles down? And the answer is generally is radioactive decay. Uranium, there's radioactive uranium, potassium, and thorium in the Earth mantle that are decaying, and when they decay, part of the decay process is given off as energy, and that is the primary heat source for the mantle. But where did the radioactive elements come from? Because they're in a constant state of decay, they may decay slowly, like uranium-238 has a half-life of 4.5 billion years, but that means there's only half as much as there used to be. And in 10 billion years, there would be almost none. So where did these come from? And you may know the answer. We talked about it briefly, but the answer is they were created. That's not the picture I wanted. They were created in supernova explosions. So if there were no supernova explosions, the mantle would probably have no heat by this time. There would be no plate tectonics. It's Goldilocks at work. You have to go back. Supernova explosions had to be before the creation of the solar system. Might be 10 billion years ago. So Goldilocks has been at work for a long time. And this is a picture of an imaginary picture of a planet, a small planet hitting the Earth, planetesimal hitting the Earth. It's widely thought that this occurred 4 billion years ago, early in the creation of the planet. It blew part of the Earth's crust out into space. Not the mantle, but the crust. This had a number of unintended consequences, one of which is it thinned the crust and made plate tectonics possible. A thicker crust probably would not move. The heat would not be able to escape. But with this thinner crust created by this planetesimal, it gave us plate tectonics. Without plate tectonics, it would be an argument, but there probably would not be life on Earth. It also heated the Earth and allowed more iron to move towards the core, which gave us a stronger magnetic field, which blocks cosmic radiation from reaching the Earth. Life on land would not be possible without this magnetic field, which was created by this planetesimal, at least arguably. Go busy. So we have this subduction. We have this spreading plate in the Atlantic, which is attached to North and South America and pushing North and South America west, and subducting, and then a spreading plate in the Pacific, so that there's ocean crust subducting all around the Pacific Ocean, creating a ring of fire. There are 452 volcanoes in this ring of fire. And the reason is this process of radioactive decay, heat rising, pushing the ocean crust apart, and subducting the lighter crust. These volcanoes, not to be trifled with, these numbers show cubic kilometers of volcanic debris blown into the atmosphere. Mount St. Helens, 1 cubic kilometer. Krakatoa, which I talked about a little bit last week, it completely blew apart. It was a large volcanic island, and it completely disappeared in 1883, 18 cubic kilometers. You get up to the size of the next one on the left, Tambora, in 1815, created a volcanic winter in 1815. I mean, industrial civilization was starting to crank up. Human population was growing rapidly by then. Many crops failed because there was so much dust in the atmosphere that it blocked solar gain on the planet. Well, there have been bigger explosions. So Toba on the right, massively larger, estimated 75,000 years ago. This is controversial. So there was Homo sapiens had evolved by that time, was at that period was beginning to migrate out of Africa, at least arguably 75,000 years ago. It's thought to have almost driven Homo sapiens to extinction, because that would have created a volcanic winter, which would have decimated the photosynthetic process, so that there was no food being made on the planet. Anyhow, this kind of thing happens, and I will mention that I mentioned the Yellowstone explosion. It was about the size, that was 2 million years ago, the largest Yellowstone explosion at the Yellowstone hotspot, which is why Yellowstone is such a fascinating place, because it is a hotspot with heat rising to the surface. It's almost as much as Toba. The number I saw yesterday was 2,500 cubic kilometers, but nobody was there. It covered half the United States in a foot of ash. that explosion 2 million years ago. 600,000 year cycle, there was an explosion 600,000 years ago, not quite as big, but plenty big. Life is tenuous affair. We need Goldilocks to be watching out for us. My favorite diagram of plate tectonics, so easy to understand. But what we're going to talk about a little bit here, so we have this ocean plate subducting under the lighter, high silica, a less dense, lighter color continental plate. What happens, the ocean plate, of course, as it gets down into underneath the continent and starts to approach the mantle, it starts to melt. What happens is it melts differentially. The elements that melt at elements and minerals that melt at lower temperatures are going to start to melt first. I think we have more of that coming up. So these are two separate pictures here. I put in Methow Valley because on the top picture, we have continental rock on the right being pushed against ocean crust on the left. The ocean crust has a piece of continental rock embedded in it, that greenish colored mountain on the left side. Sediments are running off the continent into the shallow sea and into the deep sea as the crust subducts. In the lower picture, that piece of continental rock, which is called a microcontinent or a terrain, crust, but it's continental rock. It's not dense and heavy the way the ocean crust is. It doesn't subduct, it gets pushed. It becomes part of the continent, and any rocks that are in the ocean that don't subduct are crushed in the process. If you look at the sediments in the sedimentary rock in the Methow Valley, a lot of the rock is ocean sediment that is turned straight up on end by this process of subduction of ocean crust and accretion of continental rock. So here are Methow formations. On the left is the twist formation, and this is at the top of the hill by the Windsor Post Office. You never see it because everybody's going 60 miles an hour, and if you get out of your car, you'll get killed. But it's so beautiful to stop and look at it. It's just tremendous. But this is marine sediment, twist formation, 160 million years old, was laid down flat, horizontal, is now turned straight up. A lot of the rocks in the Methow are turned straight up because of this. And you may recognize that hill. I think Kelly Graham told me that his daughter calls it the birthday cake hill because it looks like a birthday cake. You know, that's Virginian Ridge. You can see it from the highway. Those are marine sediments in Virginian Ridge, and they were laid down flat. They never quite make it to 90 degrees. They seem to like 80 and 85 degrees. Very common throughout the Methow, and it's from this story. But to return to the comment I made earlier, there were no continents. There were cratons early on. The blue here represents the ancient continental land masses, but they don't represent what exists today. So the tan is the extent of continental rock today. Where did it come from? And that's our question for the moment. And the answer it came from partial melting during the process of subduction. It doesn't show up real well here. I circled it with a 0, fractional melting. So there we have ocean crust subducting again under a continental rock. It's not all going to melt at once. It's not going to go straight to 3,000 degrees. It's going to go to 100 degrees, 500 degrees, 1,000 degrees. At 600 degrees, this high silica rock starts to melt, gets hot, it starts to rise. It rises up and becomes a massive rock in the continent called a batholith or a pluton, or it makes it to the surface and becomes continental rock, often high silica rock. Mount St. Helens was rhyolite. Another trait, and we could have shown it in that little graph I had, a little chart, of high silica rock is it's viscous, which means it's thick, it doesn't flow. St. Helens was rhyolite, wouldn't flow. It just swelled up, and then it blew up. As opposed to basalt, which flows not like water, but it flows plenty liquidy, lower in silica. Basalt is lower in silica. High silica, the rocks won't flow. Anyhow, this process of fractionation partial melting over the past 4 billion years is where the continents came from. And so it's now thought that the continents have expanded greatly in the last 4 billion years. And there was a burst of continental growth, according to some sources. Nobody was there. It's going to all be argued. 2 billion years ago. What was happening? What else was happening on the planet 2 billion years ago? The atmosphere was filling up with oxygen. And there is some suggestion that there's an interplay. So the oxygen in the atmosphere is put there by life. The oxygen is affecting the growth of the continents. Can't actually nail down exactly how at this moment. I have to read the article that I wrote in the Methow Naturalist, but it was 10 years ago and I forget. But the fascinating thing is the likely interplay of the biosphere and the geosphere here. And I should have read that article, but don't have it. So we're saying that geology, arguably, is all about silica. Granite, 70% silica. It's mostly silica. Granodiorite, so this, you're going down, you're getting slightly heavier elements. It's still 65% silica. Diorite, 60%. Gabbro is a dark rock, probably looks like that, or peridotite. Gabbro and peridotite, I'm not sure you could ever find them, or rarely find them on any continental surface. They're very high in iron, very high in magnesium, but they're still 50% silica. Silica is just a major player. So we're almost at the end, but we're still doing geology and building these continents. And we have mentioned, so we have these fragments of continental rock embedded in the ocean plate. This is not a particularly neat process. Even though it's an orderly universe, there's lots of disorder going on. And so fragments get ripped off the continents and float around on the ocean crust for a while, but they are continental rock. They're called microcontinents or terranes. They move on the ocean crust, which is moving towards the continent, subducting, gets pushed, that terrain gets pushed against the continent, does not subduct. It gets welded onto the continent. Geologists actually talk about it. They say the terrain docks like it's a ship. But the amazing thing is here, this is the west coast of North America. All those different colors are terrains that accreted onto the North American continent over the last 200 million years. So the whole of Western North America is made up of terrains. I had to pause there thinking of the Columbia Plateau is basalt, which has poured out in place, did not come in on a terrain, but it may have covered a terrain. It was terrestrial land. It was continental rock at the time. So there may be a terrain under all of that basalt. Anyhow, the point here is look at what a big process this accretion of terrains is. It's a major player in the growth of continents over time. So we have a universe that likes to self-assemble at times. And what does that mean? It means there's nobody pulling the levers. It's built into the structure, the atomic structure of the elements to self-assemble. And I'm referring now back to the shells, that there are shells, that these shells have rigid rules, two electrons in the first shell, 8 in the second shell. They want to be full. I suppose it's because of electromagnetic energy, and it causes elements to join together into minerals, and the minerals join together so that over time we get this universe that has self-assembled. I'm looking now for, so I read this quote. I like it. I read it last week. This is Ilya Prigogine, who Nobel Prize in Chemistry. He's talking about this self-assembly and this orderliness of the universe, the statistical probability that the most precisely harmonized reactions that typify living organisms would be generated by accident is 0. We're talking about a level of refinement that is beyond measure and beyond comprehension. And all I'm saying is it's an orderly universe. That's all. So we want to move on to life. I have two cartoons here. Nice way to approach the subject of life, the origin of life, because in fact, we do not know. As far as I am concerned, we do not know how life originated. I had that quote last week by another Nobel Prize winner that said it may be an inevitable aspect of the orderliness of the universe. Everything's so orderly that things just start plugging together. So this cartoon, God is making snakes, and he says these things are a cinch because all he has to do is roll them and lay them on the table. So that's, that is one idea for how life was made, and I must say, let's see, I guess it's both in those two things that I'm looking at right now, the David Christian video and Bryson. They emphasize, and I mentioned it early on, people wanted the planet to be static. That all life was created by God 6,000 years ago, and it has not changed. And the truth of the matter is, of course, the exact opposite. It is said that 99% of all living things that ever lived are extinct. They constantly, in a constant state of change. The planet is constantly changing. Life is constantly adapting. It's the exact opposite of the way we want it to be. Another cartoon. So people in 1952, a famous experiment, Miller and Ray tried to see how far they could get in a flask. And they got organic chemicals, which means carbon-based chemicals, actually. They didn't get life, but this is a little cartoon where this little living thing came out of this process of trying to create life in a flask, and he wants to know who his mommy is. And the actual situation is we do not know. But life arose. So it arose from the dynamics of the earth. So that's a piece of gneiss, which is a metamorphic rock similar to granite. It tends to have lines in it. Gneiss is G-N-I-E-S-S. Many of you know gneiss. Make a lot of jokes about gneiss rock. It's just a representation of the earth. The earth is made out of rocks. Across the earth, there's rocks and gas in the atmosphere. Somehow life emerged from that combination. So those are bacteria. That's a electron microscope picture of bacteria in the upper right. And now we have whales. That is a bowhead whale. Largest animals that have ever lived on the planet. Maybe not a bowhead, but a blue whale is the largest animal, somewhat larger. It arose from the earth. To me, it's a mystery at best. It's also worthy of creating goosebumps. It's mystical, and it's worth, I think, observing. So what is life? So next week we talk about the radiation of life on the planet, by which I mean the diversification of life. And there's a couple of pictures here of the tree of life. But what characteristics of life? You can find different lists. Life self-assembles. Well, so does granite. Life is sentient. All life responds to its environment in some way. Bacteria respond to light and dark, heat and cold. Life acquires energy to maintain an internal environment that's out of equilibrium with the external environment. I find that very interesting. We are semi-permeable membranes. Our cells are semi-permeable, our skin is semi-permeable, and we are out of equilibrium, like that those numbers I showed for carbon. What was it? 1,000th in the Earth's crust and 60% in the human body, dry weight, out of equilibrium. Life is made of cells, interestingly enough, and which are semi-permeable membranes, which let some things in and keep other things out. Life reproduces, passes traits on to offspring. Life adapts. It changes over time. It lives on a dynamic planet that also changes over time. In a way, life is a reflection of the dynamics of the planet. There are 6 kingdoms to life. That's the most popular version. There are other versions. There are larger numbers. It used to be, I don't know, what was it when we were kids? It wasn't 6, it was less. But it was 4 or 5 or 3 or 4. Anyhow, what are they? Well, the first 2 are microscopic. First one is archaea. You could call it, it's bacteria-like. They're bacterial-like cells, but most of them are anoxic. They live without oxygen. Oxygen will kill them. We have them in our stomach, archaea organisms, but they're killed in the presence of oxygen. There was no oxygen. The word means ancient. Archaea means ancient. There was no oxygen in the early atmosphere. It's all been put there by life. Bacteria, second. Well, we'll just fill them in. Protists. So protists are largely single-celled organisms, but they have a very different kind of cell than bacteria and archaea. And we'll talk about more about that next week. But they're made up of, they're much more complex with membrane-bound organelles inside the cell, even if they're one cell large, like our mitochondria and things like that. Fungi, plants, animals. This is a very simple representation of the tree of life. Here's a more complex representation. It is a very complex process. We don't know how many species there are on the planet. 10 to 20 million is the current guess. Nobody can count them. 1.4 million have been identified, but it's a big job. But this is, and so in the center left, there's one starting point. It does appear that life originated only once, and all this radiation into 10 million species came from that original life form. So all life is, scientifically speaking, related, interrelated. So going back, we saw this, I just like this picture so much, that this whole story is unfolding on a mote of dust floating in a sunbeam in space. That's Carl Sagan's description of the Earth. There's the mote of dust. Maybe we should only take it so seriously and no more so. And that quote, it's from a good movie. I couldn't remember the name last week. The movie's called Planetary. And really it's a lot of it is reflections on how being in space affected the perception of the astronauts from all different countries. So I don't know if it's online. I have a copy of it. I could give that to you on your thumb drive if anybody gives me one, along with David Christian. It's a good movie called Planetary. But in that movie, someone points out, we don't live on the Earth. We are of the Earth. We are made of the Earth. We are made from the elements and minerals and dynamics of the Earth. And I do get goosebumps when I think along those lines.